Question number 6 on the homework set looks at James Bond, and well, James Bond is imprisoned in a prison cell by one of his captors, one of his enemies, and he has three modes of potential escape. One is a air conditioning duct, one is a sewer pipe, and one is a door which is ironically unlocked. So if he just walks out the door to begin with, he's fine. But he doesn't know which one's which, and so he chooses each and every one of them with equal probability. The funny thing is that if he goes to the air conditioning duct, it takes him 2 hours. If he goes to the sewer pipe, it takes him 5 hours. But the funny thing is that if he uses any one of those other two modes of escape, or what he thinks might be escape, he comes back to the same room, but he forgets that he used them because he falls on his head. So he has a sudden bout of amnesia, and he suddenly forgets that he just chose one of those paths. So it's as though he's restarting his decision-making process. So he actually again then chooses one of those three options with equal probability. So how do we find the expectation? Or, well, yeah, when it says on average, in this case, like what is the expected value of the amount of time he takes to escape? How do we find this out? So first, let's define our random variables. T is the RV denoting number of hours to escape. Right? So how do we look at this problem? Well, the simplest way to look at it is to realize that each time he takes an incorrect pathway, he restarts again, completely forgetting what he did previously. So it's as though his entire situation is reset. And so if he takes 5 hours to go through an air conditioning duct or the sewer pipe, and when he reaches back again, the amount of time he takes from then looks the same as when he started 5 hours ago, because nothing has changed. Everything is exactly the same. So the expected time he takes to finish to escape after he takes one of the incorrect pathways looks exactly the same as it did before he took one of the incorrect pathways. So that way we can try to write something like a recursive relationship. So you have expectation of t is equal to, well, how often does he take the 2-hour pathway? 1/3 of the time he takes 2 hours plus reset, and 1/3 of the time he takes 5 hours plus reset, and 1/3 of the time he takes 0 hours and he escapes. So what exactly is there in this reset? How much time does he take after he resets? How much expected time does he take after he resets? Well, it's exactly the same as what he started off with, because nothing has changed, right? Everything is exactly the same. He has amnesia, so he completely forgot what he did. So the probability of using one of those incorrect pathways still remains the same. And therefore, we have expectation of t is equal to 1/3 times 2 plus expectation of t plus 1/3 times 5 plus expectation of t plus 0, right? Which is equal to, let's say, 7/3, right? Taking only the 5 and the 2 out, plus 2/3 expectation of t. So now pulling this to the other side, we have expectation of t minus 2/3 expectation of t is equal to 7/3, which implies 1/3 expectation of t is equal to 7/3. 3 and 3 get cancelled. Nope, it's 2 over. Yeah. So the expected amount of time he takes is equal to 7 hours. So you do, like, this isn't the standard formula for expectation, right? This isn't the natural form for expectation, because what you've either seen for expectation is the linearity of expectation, or you've seen the actual definition of expectation, which is the sum of all sample points times their probability, weighted by their probability. But so in this case, you shouldn't think of expectation of t as you shouldn't try to calculate expectation of t by the formula you have. Just think of expectation of t here as a different variable which you're trying to calculate, which is the average amount of time he takes to escape, right? So he takes some amount of time to escape, and in one third of the situations he takes 2 plus the same amount of time, plus in one third of the situations he takes 5 plus the same amount of time, right? And in one third of the situations he takes no time at all. So we get the recursive relationship, which gives us this. Now there is another way to look at it, which is slightly more complicated. Well, it's much more complicated, which tells you exactly how to do it using the definition and the formula which you're expected, which you're used to. And I'll just give an outline of that right here. So the way that works is that, well, let's take, let's say R to be the number of turns till escape. And what do I mean by turn? A turn is if he chooses an air conditioning duct, that's a turn. If he chooses sewer pipe, that's a different turn. If he chooses the door, it's a different turn. So the number of turns he takes to escape. What is this? So this is a geom. I'm going to put that separately. So R is distributed as a geom, right? Geom with probability 1/3, because every single time he has a probability of 1/3 for it to be the final turn, in which case he chooses the actual door to escape, and otherwise he fails with probability 2/3. And now let's consider the situation that he fails. Given that he fails, how much time does he take? So let's say x of t is the RV, is the RV representing number of hours spent on round t. So given that he fails on that round, because if he doesn't fail, xt is just going to be equal to 0. Let's just say he fails. Given that he fails, this is xt is equal to 2 with probability half. With half now, because you know that there doesn't fail, then the probability of choosing each and every one of those, or either one of the two incorrect pathways, is just going to be a half. Or it's 5 with probability half. So what is the expectation of xt? Which is just equal to 7/2, right? So now we want to find out the expectation of sigma I is equal to 1 to R x of t, right? That's what you're trying to find, or rather R minus 1, because he fails in the rth round. How do you do this? So this is going to be equal to expectation of xt for any given t times expectation of R minus 1. So this is this might seem as a far-fetched this might seem as a stretch, but what you actually can do is you can easily prove this by just using the formula for expectation. Well, okay, why don't I just run you through the proof on the left hand side? Let me just erase that out. So I've written out what we're trying to calculate over here. So this uses something, this uses an idea called conditional expectation, where consider a set of events which partition the sample space, let's say like a pie or something. That last one didn't look nice. I'm just going to draw random stuff, right? So this is A1, A2, all the way till A8, right? So if you have a set of events which partition the sample space, what does that mean? The union of all AI over I is equal to the intersection, is equal to the sample space, and the intersection of AI comma AJ, where I not equal to J, is equal to the null set. So basically they don't intersect each other, but together they form the entire sample space. If you have events like that, the expectation of some random variable b is equal to the sum over all AI expectation of b given AI times probability of AI. So you don't need to know this, but it's actually very simple to prove, and it's very simple to find out. But yeah, so if you have a bunch of disjoint events, then the expectation of a random variable is equal to the expectation of the random variable conditioned on getting an AI, or like conditioned of, let's say, B is somewhere there. So the expectation of this is the expectation inside this multiplied by the probability of getting A1 times this one multiplied the probability of getting A2 all the way. So the expectation is, this is just like conditional probability. So the expectation of B is equal to the sum over all AIs, expectation of B given AI times probability of AI. So this is using conditional expectation, we can prove this, right? So how do we do that? Let's look at this. So now the AIs in this case are going to be the events corresponding to the different values that R can take. So basically an event AI is going to be R is equal, A1 is going to be R is equal to 1, A2 is equal to be R is equal to 2, is the event that R is equal to 2. So let's just, and so on, let's just do that now. Infinity looks weird. Okay. Expectation of summation of I is equal to 1 to R minus 1 xt given R is equal to k, right, times probability that R is equal to k, which is equal to, now we know that since xt, like since all the xt's are independent of R, right, the xt's don't care about what value R takes, right, because the xt is just going to be half, is just going to be 2 with probability half and 5 with probability half in any given turn that that you've not yet, that James Bond has not yet escaped. So this is just going to be equal to, how many times are we going to find this? So basically this entire part is just going to be k minus 1. This entire part is just going to be k minus 1 times expectation of xt, right, because you're summing over I is equal to 1 to R minus 1, and all the xt's have exactly the same expectation, or they all look the same. So by linearity of expectation, you break this up into k minus 1 different xt's, and the given R is equal to k just vanishes because xt is independent of the number of times James Bond tries again and again to escape, times probability of R is equal to k, right, which is probability that R is equal to k. Now let's pull the expectation of t out, because t does not depend on k at all. So this is equal to expectation of xt times, I'm just going to move this aside, times sigma k is equal to 1 to infinity k minus 1 times probability that R is equal to k. Now what is this expression? This expression is exactly expectation of R minus 1, right, because this is the probability that this is the summation over all cases where you're taking k minus 1 times the probability of R being equal to that k. So this is just exactly the expectation of the random variable R minus 1, or some random variable which is equal to R minus 1. And this is exactly what we've proved. And using conditional expectation, we found that the summation over here, because R and xt are independent, we have expectation of the summation from I is equal to R minus 1 xt, R minus 1 to I is equal to 1 to R minus 1 xt is just equal to expectation of xt times expectation of R minus 1. So what is the expectation of xt? We've calculated this to be 7 over 2. What is the expectation of R minus 1? Which is just equal to expectation of R from linearity of expectations minus 1, right? And this is equal to, what is expectation of R? I think since we calculated that it's a geom, so the expectation of R is just going to be 1 over the probability of the 1 over the parameter of the geom, which is 7 over 2 times 1 over 1 over 3 minus 1, which is equal to 7 over 2 times 3 minus 1, which is equal to 7. So we got the same answer using a more rigorous proof using conditional expectation. And since you guys haven't seen conditional, I don't think you've seen a conditional expectation yet. Maybe you have. So the other proof would have definitely been simpler. But I just gave this because maybe you would think that I don't get why you could just multiply expectations just like that without using the formula for expectation. So I decided to put down this proof too, which I guess uses formulas which you're slightly more used to. Yeah, that's about it for question 6.